Okay, we have characterized the bijective linear transformation from vector space V to a vector space W. Okay, and such a linear transformation is called an isomorphism. From V to W. Right? And in this case, we will call V and W are isomorphic to each other. Okay? Okay, so now isomorphism between vector spaces have the following properties. Okay. The first one is reflexivity. Okay. All right. So reflexivity means that any vector space V is isomorphic to itself. Okay? All right, so a proof is like this one. Consider the identity mapping. Okay, so we consider identity mapping. Right, so this is identity mapping. And you can see that identity mapping I'm sorry, and I find a typo error. So this should be V and V prime. Okay, so this alpha V plus beta V prime. Okay, and this is alpha identity of V plus beta identity of V prime. For all V prime in V alpha scalars and the scalars alpha and beta. Okay, so that identity is an isomorphism so it's a bijective linear transformation okay, so and it is a bijective linear transformation from V to V. Okay, so this one is to check that ID is linear, right? The linearity of the identity function, and the identity of course is bijective, right? We know that before. So ID is a projective linear transformation. So V is isomorphic to itself. Right, so the first one is reflexibility. The second part is symmetry. If a vector space V is isomorphic to a vector space W, then W is isomorphic to V. Okay. All right, so now V is isomorphic. So V is isomorphic to W if and only if there is a an isomorphism T from V to W. Right? So now if T is an isomorphism from V to W, then T inverse is an isomorphism too. Because T inverse is also linear. Right? We just proved that T inverse is also linear. So that it's invertible and linear, and so it's an bijective. So this says that the W is isomorphic to V. Okay, so we have done. So this is symmetry. And the third one is called transitivity. If V is isomorphic to W and W is isomorphic to Z, okay, where V, W, Z are vector spaces. Okay, so if V is isomorphic to W, W is isomorphic to Z, then V is isomorphic to Z. So this is called the transitivity. You can transit the relation. Okay. Okay, so V is isomorphic to W, and W is isomorphic to Z. This implies that there exists a T from V to W and S from W to Z. Okay? which are isomorphisms. Okay. And then the composition. Then consider, so now we consider by Theorem 5.2.b that the composition of T and X, right, is a linear transformation. Okay, so we prove that composition of two linear transformations is also a linear transformation. Okay. And now we have to show that this composition is an isomorphism. To show it is an isomorphism, we have to show that it is bijective. And to show that it is bijective is to show that it's invertible. Okay, so we try to find an inverse of them. Right, so we guess the inverse of this composite is this one. All right, so we check. And this identity is a W. Okay. And this is an identity of V. Alright, so we get that one. And we check the other way. And what is that? So this is again, this is the identity mapping of W. So this is X, and this is the identity mapping of Z. Okay, so that this composite is invertible, and then bijective by Theorem 5.2.a. Okay, so that is invertible. Right, so it's an isomorphism. Okay, and then V is isomorphic to Z. Okay, so isomorphism has these three properties: reflexivity and transitivity, and symmetry. All right. Okay, so 1, 2, 3. Reflexivity, symmetry, transitivity. So we can summarize. So it's just like the row equivalence we discussed in chapter 1, that for two row equivalence is a relations on matrices, and we find that row equivalence has so they have the three properties, and any relations satisfying the three properties is called an equivalence relation. So that we have a theorem 5.2.5, the relation of isomorphism between vector spaces is an equivalent relation, right, on the collection of all vector spaces. Collection means set, but sometimes we don't use a set because we use a collection, but the meaning is the set, okay? Okay, so this is a summary that isomorphism is an equivalent relation. All right, so now we recall a result. A linear transformation T from N to Rm, or from Cn to Cm, has a unique matrix representation. T of x equal to ax for all x in Rn or Cn, okay, where A is an m times n matrix. This has been shown in Theorem 2.3.2 in chapter 2. Okay, so we have shown that any linear transformation from Euclidean space to another Euclidean space can be represented by a matrix A. Okay, so the image of X is just the multiplication of the X by a matrix from the left-hand side. Okay, so we just recall this one. So now I prove a property. So we let A be an n times n matrix which represent an isomorphism from Rn to Rn or from Cn to Cn. Right? So suppose that A is the matrix, and this matrix represents an isomorphism. Okay? Then A is invertible. Okay? And its inverse, A inverse, is the matrix representation of the inverse oh, I forgot to put T. Okay, so A represent an isomorphism T. So if A represents an isomorphism T, then A is invertible, and its inverse also represents the inverse of T. Okay, right? So that is the idea. All right. So the theorem is quite natural, right? A represents an isomorphism T. Then its inverse, then A is invertible, and then its inverse represents the inverse of T. Right, but we still need a proof for this result. So we let B be the matrix representation of T inverse, right? Because T is an isomorphism, so its inverse exists, okay? Then the matrix representations of T composite with T inverse composite with T, and T composite with T inverse. So these two composites are B, A, and AB respectively. Right? We proved that by theorem 2.3.8 plus 9. Okay, so in chapter 2 we proved that before, right? So the matrix representation of the composition of two linear transformations on Euclidean spaces becomes to the product of their matrix representations. Okay, so we proved that before, right? So we just use this theorem here. But we know T equal to T is the identity of Rn or Cn, right? So it's the identity mapping, and which has identity as the matrix representation, which has the identity mapping has a matrix representation, identity matrix. So that but in here from theorem 2.3.8 plus 9, these two linear transformation has a matrix representation BA and AB, so that immediately we have AB equal to BA equal to this one. Okay, and so B is equal to A inverse. And B is the matrix representation. B equal to A inverse. So A inverse is the matrix representation of T inverse. Okay, and we have done. Okay. Okay, so now we will have a series of theorem about basis. If a vector space V has a finite basis, then all of its bases have the same size. Okay, so if a vector space V have a finite basis, then all its bases have the same size. So let B be a finite basis for V, and the size of V is n. Okay, so it's a finite. So we let the size of B is n. Now we let C be another basis for V. Our purpose is to show that C is finite and has the same size as B, which is n. Alright, so now since V is equal to the span of B, okay? So B is a spanning set of C, and the C is a subset, a set of vectors in the span of B, okay? Alright, so span of B is V, so that C is a set of vectors in the span of V. Alright? And then so we must, so because of this property, and because C is a basis means that C is linearly independent, so that so we must have the size of C less than or equal to n. Why? Because if not, otherwise C is linearly dependent by theorem 2.4.10. Okay, so we have to review what is theorem 2.4.10. Okay? So let x u1, u2, un be a linearly independent index set of vectors in a vector space V. Okay? So suppose we have a linearly independent index set of vectors in V. Oh, not necessary. Okay, sorry, I have to. Okay, not necessary. Just this is more so that just say that let's be a subset of n vectors in V. Okay, any can be linearly dependent or linearly independent, just a subset. Then every set of more than n vectors in the span of S must be linearly linearly dependent. Okay, so the theorem is very useful and quite general. It's just a subset of n vectors, so you have n vectors. Okay, there. And then if you pick up vectors from the span of S, okay, you pick up, and if you pick up more than n vectors, okay, say n plus 1 vector or n plus 2, or even infinitely many vectors from the span of X, then this set must be linearly dependent. All right, so now the basis is a set of vector from the span of B. So B is just like the S, the set. Yeah. And B has n vectors, of course. So B has n vectors. And the C is just a set of vectors from the span of this. Okay? Now, if the size of C is greater than n, if the size of C is greater than n, more than n, then the set should be linearly dependent. Right? So but we know C is linearly independent. So if the size of C is greater than n, then C is linearly dependent, which is a contradiction to C being a basis. Okay, so so we must have the size of C less than or equal to n. Otherwise means that if C greater than n, otherwise it means that if C greater than n, then C is linearly dependent, and this is a contradiction. to C being a basis. Okay? So immediately we know that the size of C should be less than or equal to n. Okay? And so we let M to be the size of C. Now we know C is a finite set. Right? So we let size of C. Again, since V is equal to the span of C, right? Because C is a basis. Right? So B is a set of vectors in the span of C. Okay? So now we change the role of these two sets. Now C becomes to the S set here. C is the S set. Okay? And C has M element, the size of, and B is a set of vector, right? All right, so we must have the size of B is less than or equal to M. Okay? Otherwise, B is linearly dependent. Otherwise, it means that if the size of B greater than M, okay, greater than M, then by the theorem, B should be linearly dependent. 4.10. But this is again a contradiction. To B being a basis. Okay, so now we have two inequalities. M is equal to the size and is less than equal to n. N is equal to that. So M is less than equal to n, and n is less than equal to m. So that n is equal to m. i.e. the C is equal to B. And this is the end of the proof. Okay. So we get a very important theorem that if a vector space has a finite basis, then any of its bases has the same size. Okay, and it's finite. All right, so we will give a name for a vector space having a finite basis. Okay. Okay, so any vector space having a finite basis will be called finite dimensional. And the size of any basis for V is called the dimension of V, denoted as okay. All right. Now, this theorem use theorem 2.4.10. Okay. Now we need theorem 2.4.12. Okay. Theorem 2.4.12, right, can be rephrased as follows. Okay. A linear transformation T from an n-dimensional vector space V to a vector space W. So the W may not be finite dimensional, just general vector space. But the domain V has to be finite dimensional, so we call it n-dimensional. Okay, so that so this is exactly theorem 2.4.12. Okay, so this linear transformation can be uniquely specified or determined by its image Wi equal to on a basis B, which consists of V1, V2, Vn for V. Okay, so you want to specify a linear transformation from a finite dimensional, here, n-dimensional vector space to a vector space W, then you can specify this one uniquely by putting the image of on a basis. So for each basis vector in the basis V1, V2 of Vn, you just put give the image or the value of Vi. Okay. And later on, we will generalize the theorem, okay, to not only the finite dimensional vector, just arbitrary linear transformation for a T from arbitrary vector space V to arbitrary vector space W. Okay. But for the moment, we just need the theorem here. Two finite dimensional vector spaces are isomorphic if and only if their dimensions are the same. So now it's quite easy to see if two finite dimensional vector space isomorphic or not. Okay? Just look at their dimensions. We proved the reverse direction first. If they have the same dimension. All right, so let B to be V1, V2 up to Vn, and the C to be W1, W2, Wn. So we select basis for the two of the same dimension. Respectively. Okay, so B is a basis for V, C is the basis for W. Okay, and V and the W have the same dimension N. Now, by Theorem 2.4.12, okay, so as I make in the remark, there is a unique linear transformation T from V to W with what? You specify that the image of Vi to be Wi. Okay, so we just map every Vi to Wi. Okay. And such specification gives us a unique linear transformation from V to W. Okay, so C is well defined. And similarly, we call S from W to V with S to I equal to Vi. Okay? So now we establish the two linear transformations by specifications like this. Now, we look at the composite. Okay, so we look at the composite of the S and T and S. So this is X, T. Now by our specification, this is Wi. And by our specification of S again, this is Vi. Okay? Alright, so you see that this implies that is equal to the identity mapping from V to V. They must be equal to the identity mapping. Why? Because for identity mapping, we'll map Vi to Vi. So identity mapping and this composite has the same specification. Okay? So once they have the same specification, they must be the same. By theorem, okay? So by theorem 2.4.12. Okay, and also here and also there. So we apply these three things is because the theorem 2.4.12. And again, okay, so I write down 4 statements, and they are valid because of theorem 2.4.12. So you can see this statement is very useful because to do the specification is very simple, right? Just assign an image to every basis vector. That would be enough to specify a linear transformation uniquely. Okay, so the first two give us, we construct two specific linear transformations, and then we check that their composite becomes to identity. So S actually is the inverse. Okay, and T is biject, is invertible. Okay, so T is invertible, right? And then bijective. Okay, so by theorem 5.2.8 we proved before. And so T is an isomorphism. Okay? When T is isomorphism, so that these two V and so V is isomorphic to W. Okay, so we finish the forward part, the backward part. Now how about the forward part? All right, so let V and the W, okay, be two isomorphic finite dimensional vector spaces. All right, and the T from V to W an isomorphism. Okay, so that so we have that. So we have two isomorphic finite dimensional vector spaces. And T is the isomorphism. And we want to show that V and the W have the same dimension. Okay. Okay, so we let B be a basis for V. Okay? And consider the image of the basis vector called C. So it would be T V1, T V2 up to T Vn, which is an indexed subset of W. Okay? So it's index of set of W. Because at this moment, probably maybe two of them would be the same. Possible, we don't know, right? So just collect the images together. Okay. But as we know, because it's an isomorphism, so that they must be distinct, of course. Okay. Otherwise, it's not an isomorphism. Okay. So that it's not necessary to put the index. Yeah. So just say, okay, it's just a subset of W only. Okay. Because they are distinct. Right? Isomorphism is injective and surjective. Okay, so our purpose is to show C is a basis for W. This is our purpose. Because if C is a basis of a W, then you can see that the size of C is n, right? So the dimension of a W will be equal to the dimension of V. And this is what we want. So they have the same dimension. Okay? So that our task is to show C is a basis. Okay, so we have two things to prove. The first claim is C span W. Okay, this is the now, since T is onto, okay, so for each W in W, there exists V such that T V equal to W. Okay, but since B is a basis, so V is in little v is in capital V, so that we can be read as a linear combination of the basis vector in B. Okay? So W okay. Now, by linearity of T of the linear transformation, so you can see that W is a linear combination of the T VI's. So this is in the span of C. All right. So every vector in W is in span C, so that W is contained in span C. Right? So this implies that W is equal to the span C. Because span C is a subset of W. Okay, so the first claim is done. Second claim. C is linearly independent. Okay, this is the second claim. Okay, so consider a linear relation on C. Okay, so we consider alpha 1t v1 plus alpha 2t v2 plus plus alpha n t vn equal to the 0 vector. This is the 0 vector in W. Oh, in W, in the vector space W here. Okay, and so we have T alpha 1 v1 plus alpha n vn equal to W. So this implies that alpha 1 v1 plus alpha n wn, right, is in the kernel of T. Okay. But the kernel of T consists of the 0 vector of V only because it's injective. By theorem 5.1.a, okay, since T is injective. Okay, so we show that in theorem 5.1.a that if a linear transformation in T is injective, then its kernel is trivial. Right, it's trivial here. Okay, so in here, but this is so that means that alpha 1 v1 plus alpha n, oh sorry, not vn is equal to 0v here. And this implies that alpha 1, they are all 0 since B is linearly independent. Okay? So for any linear relation, we find that all the coefficients must be 0 so that C is linearly independent. Okay? So from these two claims, so from both claims, C is a basis for W, and the dimension of W is equal to the size of C, is n is equal to the B, and its dimension of V, and we have done. Okay. Okay. So now we take a short break up to 11:20. Okay, for our purpose, we need a technical lemma. Okay. All right, so X is a linearly dependent set of at least two vectors in a vector space. Okay, so the S is a linearly dependent set of at least two, right? So it's linearly dependent at least two vectors. Then some vector means one vector, right? So then sum, okay, in S is a linear combination of other vectors in S. Okay. The set may be infinite. Okay, so just require it consists of at least two, but the set may be infinite, and the S is linearly dependent. Okay, so so we can pick up a vector in X, and this vector will be a linear combination of other vectors in X. So this is a very technical lemma. Okay, so since S is linearly dependent, okay, so there exists a non-trivial linear relation by definition, right? So we have a non-trivial linear relation. Okay, for distinct vectors. So the vectors, they are all distinct. U1, U2 up to Un in S. And the scalars alpha 1, alpha 2 up to alpha n, not all zeros. So we says alpha I not equal to 0. So we say that alpha I not equal to 0. Okay. Now, if n equal to 1, it happen that the number of terms in the left hand side is only 1. Okay, so if n equal to 1, then alpha 1 must be non-zero because there is only one coefficient, right? And so the alpha 1 should be non-zero. And if alpha 1 is non-zero, this is the zero vector, right? So that U1 must be the zero vector. There's no other choice. Because if alpha 1 is non-zero and U1 is non-zero, then this product is non-zero. Okay? It's non-zero. Right? So if n is 1, then we must have this result. Now, since X has at least two elements. Alright? So there is a vector in X other than the 0 vector, because U1 is 0, right? Okay? So we can pick up, because we know 0 vector is in S, right? And but X has at least 2 elements. So there is another vector other than 0, and we call this vector U2, okay? And we form a non-trivial linear relation on S, like following. Alpha 1 U1 plus 0 and the U2 is equal to the 0 vector. Okay? And so the 0 coefficient is actually alpha 2. So this is alpha 2. Okay? So now we have a non-trivial linear relation, right? Again, because alpha 1 is non-zero. So this is a non-trivial linear relation. Okay? So the reason why I did that is because that if the linear relation is too short, so that the only one term here, then we can replace that linear relation, that non-trivial linear relation, by this one. And so the n is 2. Okay. So n is 2. All right, so that we always have a non-trivial linear relation, okay, on S with n greater than or equal to 2. Okay, so we will have a non-trivial linear relation with n greater than or equal to 2. So at least 2 terms here. Okay, now at least 2 terms there, and therefore we have, because we assume alpha I not equal to 0, so we have ui is equal to minus alpha 1 ui alpha I u1 okay, so we can move at least 1 term to the right hand side, because when n is equal to 1, there is no term can move to the right hand side, right? So this is the reason why we require that such a linear, non-trivial linear relation has at least 2 terms. All right? And when they have at least 2 terms and one coefficient, say alpha I non-zero, then except the alpha I ui, we will move all other terms to the right hand side. So that we have this expression. So we have this expression, and So which shows that a vector means ui in S is a linear combination, okay, of other vectors in S. Okay, so we have this technical theorem here. Okay, if S is a linearly dependent index set of at least two vectors in V in the vector space, okay, so maybe I will say it, a linear dependent index set of vectors in a vector space and with n greater than equal to 2. So in the list, n is at least 2. Then, by definition, so we have a non-trivial linear relation on S. Okay, so it's alpha 1 U1 plus alpha 2 U2 plus da 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 plus alpha n UN equal to the 0 vector. For some scalars, alpha 1, alpha 2, up to alpha n, not all zeros. Okay? Alright, so now automatically, because when the index set has n, the length, n greater than equal to 2, so that we have at least 2 terms here in the left hand side. Okay, so if say alpha I not equal to 0, then ui, okay, is a linear combination okay, of u1 up to ui minus 1, ui plus 1 up to un. Okay? So again, still, there is one element here in the index set can be expressed as a linear combination of all the other elements. Okay. Okay, and so this technical lemma actually valid for linearly dependent index set. We have to deal with such an index set separately because that their members may be the same. Okay, they may be the same. So that we have to do it differently. Okay, so the theorem will be called removing an element. So X, a subset of a vector space. Right? So suppose we have a subset. Now, so let V in S be a linear combination of other element in S. Suppose we have in this set we can find a vector V. This vector is the linear combination of other vectors in S. Okay. Then we have the span of S is the same as the span of S removing the element V. So if we remove V from S, so that S becomes smaller, but their span will be the same. Okay? So this is the way to reduce the size of a set without change its span. Okay? This gives us a condition for that. All right, and the proof is that it is clear that because this say is smaller than this say, so that the span of S removing V contained in the span of S, of course. So the next thing is to prove that actually any element in the span of X is also in the span of this smaller set. Okay, so that now since V in S is a linear combination alright, since V is equal to, say that beta 1 V1 plus beta n Vn for some other vectors V1 Vn in S and scalars beta 1 up to beta n. Okay? Now for an U in the span of X, so we have now U is equal to alpha V plus alpha 1 V1 plus alpha n Vn plus gamma 1 V1 plus gamma up to gamma k UK for some U1 up to UK in S different from V1 up to Vn, and for some scalars alpha 1 up to alpha n, gamma 1 up to gamma k. Okay, so V itself, we say that it's a linear combination of other elements. So V1, V2 up to Vn are different from V. Okay, and consider an arbitrary element in the span of X. In the span of X, so we can express U as linear combination. Okay, so specifically we put the alpha V here. Alpha may be 0. So if alpha is 0, then it's not, can be regarded as not a combination. So so V will not contribute to this contribution. But it's fine that to put the alpha V here. And also could be related to V1 up to Vn. But could be, we need the other vectors U1 up to UK, different from V and the V1, V2 up to Vn, all right, to make contributions. Okay, so the generic form for an U in the span of X would be like this one. Okay, but if this is okay, then we can do the substitution, so that this substitution will go to here. All right, so now we have alpha 1 plus alpha beta 1 V1 plus alpha n plus alpha beta n Vn plus gamma 1 U1 plus plus gamma k UK. Okay. So now U can be expressed as a linear combination of elements U1, V1 up to Vn, U1 up to UK. So this is in the span of S, but remove V. Because that V1 up to Vn, U1 up to UK are distinct vector in S, and distinct from the vector V. Okay. So that this shows that the span of S is contained in the span of S. Remove V. Okay? Here. So we have this one as this one. So finally, the span of S is equal to the span of S remove V. Okay? So we have the final result here. Any questions? All right, V an n-dimensional vector space S a set of n vectors. Right? Such that V is equal to the span of it. Right? So we have two data. One is that V is an n-dimensional vector space. The second data is that X is a set of n vectors in V such that V is the span of S. Okay? So S is a spanning set, right? And S has n vectors. Then X is linearly, then, oh, okay, just say that. Then S is a basis for V. So the conclusion is that in general, to show that a subset of V is a basis of V for V, we need to check two things. One is that the set should span V. The second is that we should to check S is linearly independent. Two things. But if we know the information of the dimension of the vector space, so we know V is n-dimensional, so we know the dimension, and we know the spanning set having n vectors exactly the same, then X is automatically linearly independent, and so S is the basis. Okay, so we have to show this one. All right. Now, if n equals to what? Suppose S V is one-dimensional, and X consists of one vector. Then X consists of a non-zero vector. Why? Because if S is consists of only the zero vector, then the span of X is the trivial vector space, consists of only zero vectors only. So it is clear that this equality is not true. Okay, so for this to be true, then X consists of a non-zero, must be non-zero vector, and it's a linearly independent set, of course. Okay, so if a set consists of only one non-zero vector, then this singleton, this set is linearly independent, and so that S is a basis for V, of course. All right, so now we let n greater than or equal to 2. Okay, so now S is a set, okay, of at least two vectors. All right, so S is a linear vector. So suppose, so we want to prove that X is linearly independent, right? So we prove this by contradiction. We suppose that S is linearly dependent. All right? Suppose this is linearly dependent. And we have this technical lemma. If X is a linearly dependent set of at least two vectors, then some vector in X is a linear combination of other vector in X. Okay, so suppose X is this case. Okay, then, so by this technical lemma 5.2.8, some vector we name it as V in S. Okay, it's a linear combination, okay, of other vectors in S. Okay, now we have the theorem here. We can remove this V, okay, without change its span, so that by theorem 5.2.8, okay, the span of S is equal to the span of S. Remove V. Okay, so we can remove V and downsize the set X without change the span. Okay. Okay. Okay, and we know this is V, right? Without changing span, so the span of this set is V. Now, since any basis C for V must be linearly independent. Okay, so C, the size of C must be less than or equal to the size of this set, because C is a subset of the span of this set. Okay, so that the size of C should be less than or equal to the size of this set. Okay. Otherwise, C is linearly dependent by theorem 2.4.10. Okay, we use that quite often, so that because if C, the size of C is bigger than the size of this set, then C must be linearly dependent. Okay, so a contradiction again. So this is a contradiction. All right. And so we have the dimension of V. Okay, so now we have N is the dimension of V, and which is the size of C, and the C is less than the size of. Okay, and this is equal to N minus 1. Okay. So this is less than N. So with the result is N is less than N. Wow, it's a contradiction again. Okay, so this is a contradiction. So we have nowhere to go. So what is wrong? Right? What's wrong is this here. But we suppose X is linearly dependent, it will get to contradiction. Okay? So X is linearly independent. Okay? And then S is a basis for V. Okay, so we have done. Now we have a symmetric theorem to the previous theorem. Okay, so V again is an n-dimensional vector space. Okay, and as a linearly independent set of n vectors in V. Okay? So now we have a set which is linearly independent, and the size of the set is n, and the n is equal to the dimension of V. Then X is a basis for V. Okay, so the proof is again by contradiction. Suppose the span of X is not equal to V. Wow, not equal to V. So we have the situation, this is V, and this is the span of S. So we can pick up a vector V out of the span. Okay? So that we pick up and V in, then it's a linearly independent set. So we can form a bigger linearly independent set by theorem. Okay? So this is the way we construct a basis, right? Starting from an empty set, okay? And we draw a vector from V one by one. If the span of the set is not equal to V, then we can pick up one. Okay? All right, so now we have this situation here. Now, since dimension of V is n, there exists a basis B, okay, of size n for V. Okay, so it has a basis. Okay, now since the set is contained in V, and this is in the span of B, because the B is the basis. Right? So that the size of U must be less than or equal to the size of B. Why? Why must be? Why this is smaller? Why? Otherwise, if the size, this is bigger than B, if it's bigger than B, then S union of V become too linearly dependent. Okay? Again, by theorem 2.4.10. Okay, so we have a linear independent set. But this is a contradiction, because that this is say already show that this is linearly independent. Okay, so we have the situation here, but the size is n plus 1, and the size is n. So we get into a weird conclusion that n plus 1 is less than equal to n, which is impossible. Again, so this is a contradiction. So what is going wrong? Where? At the beginning. At the beginning that we suppose that the span of x is not equal to v. We get into contradiction. All right, so that the span of S must be equal to V. This implies that S is a basis for V. End of proof. Okay, so again, from the theorem, the data is that if we know that the dimension of V is n, and we have a linearly independent set, and the size of the set is also n, then automatically this set span V, and so that S is a basis for V. Okay, so that is the information we have. Okay, so now if a set of n vectors spans a vector space, suppose we find a set of n vectors span a vector space V, then the dimension of V will be upper bounded by n. Okay, so we will have a bound there. All right, so the proof is like this one. Suppose be a set of n vectors okay, it's a set of n vectors in V. Now, if V is not finite dimensional, oh, no, sorry. Okay, vectors which spans V, i.e. okay, we have this one. Now, if n equal to 1, then if n equal to 1 means that x has 1 vectors, then S consists of a non-zero vector. Okay, and it's a linearly independent set. So that S is a basis for V, and the dimension of V is equal to 1. Okay, so this is equal to less than equal to 1. So that is true, right? So 1 is less than 1. Okay, so if the set consists of only one vector, then this set must be a basis. Okay, and so the dimension of V is 1 and less than 1. So the theorem is true. So now we let n greater than equal to 2. Okay, and so if x is linearly dependent, okay, so if x is linearly dependent, then some vector v in x is a linear combination of other vectors in S. Okay, by our technical lemma 5.2.8. Okay, right, so we have and by removing V from S, so by moving V from S, okay, we still have V is equal to the span of the smaller set. Okay, by theorem 5.2.8 here. Okay, so we can remove. So we can, so if the resulted set still linearly dependent, then we can remove them, right? One by one. Okay, so we continue. So we continue removing vectors one by one from the resulted spanning set. Okay, if it is not linearly independent. Okay? So every time when we resulted a spanning set which is linearly dependent, then we will remove one vector from the resulted spanning set, one by one. So we will stop because the things, the size of S is n, the process will stop, right? At the most n-1 steps. Why? Because if you remove the n-1 vectors out from the x, then you will have only one vector left. And then you go to the first case. Okay, you go to the first case. And so the set x is linearly independent because it's only one vector. Right? So you get a linear, or you stop earlier, means that you already have linearly independent set. Okay? Okay, so you will stop in at the most advanced one step, and linearly independent, subset Q of X, right, is resulted. With V is the spanning set of Q. Okay? So now, so that's Q is a basis for V. Okay? And then, so the resulted set Q is a basis for V. And then the dimension of V is equal to the size of Q, and the size of Q is, because Q is a subset of X, so the size of Q is less than equal to the size of X is equal to N. And we have done. Alright, so that we get this result by using a procedure. Okay, this procedure is to removing one vector one by one. Okay, to get them. Okay. And the theorem has another symmetric theorem. Suppose that if there exists a linearly independent set of n vectors in a vector space V, then either V is not finite dimensional, or the dimension of V is greater than or equal to n if it's finite dimensional. So the proof is simple, that if V is not finite dimensional, then we have done. So we have done. Okay, so if V is finite, it's not finite dimensional, we have done. So that we will assume that V is finite dimensional. Okay, and has a basis B. All right, so now let X be a linearly independent set. Okay, of n vectors in V, but V is now in the span of B here. Okay. So now we must have the size of X should be less than or equal to the size of B, because S is the linear independent set in the span of B, okay, and so that and because S is linear independent, so that this inequality must be true. because otherwise X is linearly dependent by theorem 2.4.10, and this is a contradiction. Okay, so dimension of V is equal to the size of B, which is greater than size of X is n. Okay, so the dimension of V will be greater than or equal to n. This is what we want here. So we have this result. Okay. All right. I think I stop here. Okay. I can't finish section 2 because section 2 is a long section. Anyway. Okay. Any questions? So the information of dimension of an infinite dimensional vector space was important information. Okay. Okay. So if no question, I will stop here, and I'll see you next week.